So the mic is on. Okay. Yeah. So thanks to the organizers for having me here. Okay. So today I will talk about so to say a uniform way of building protocols for classical and quantum communication tasks that we have recently developed. Now our motivation originally was mainly to tackle quantum tasks, but what I'll do today is I will describe the corresponding classical counterparts of the tools that we developed to handle quantum tasks, and then maybe exhibit a few a few protocols for some of the tasks using these tools. Okay, so what are these tools? Okay, so one is what we call as convex-split lemma, and this can be seen as some kind of operational sort of. This kind of gives some kind of operational meaning to what is known as Dmax, that is the max relative entropy. Okay, and the other tool is what we call position-based decoding. And this, so to say, gives operational meaning to DH, okay, the hypothesis testing divergence. So the Dmax and the DH are sort of at the two ends of the spectrum, right? Both of them converge to relative entropy, but in the one-shot setting, they sort of occupy at the two ends of the spectrum. Okay. All right. So let me start by describing what these are. Okay, so in the classical setting, we can okay, so let's consider a scenario where we have say two joint random variables x, y. Okay, and then several other independent random variables. Okay, qy1 q. So yeah. White is okay, or I should use yellow? Huh? Oh, I see. Okay, okay. Oh yeah, okay. So So what is the setting here? So we have two random variables x, y distributed according to some joint distribution P. Then we have independent random variables y1, y2 up to yn identically distributed according to some distribution Q. Okay, and so x, y are correlated, but then the rest all are independent and independent of x, y. Okay, so this is one sort of component of our convex mixture that we'll create. All right. So in the second component of the convex mixture, the first and the third random variables are jointly distributed according to P, X, Y, and the rest of them are distributed according to Q. No, not necessarily. So that's why I'm using a different letter. So QY is not necessarily the marginal PY. No, there it is. So in this component, first and third are jointly distributed according to PXY, and the second and the rest are according to Q, where Q could be different from marginal of P on Y. And then here it is the first and the last, and the rest like that. Okay. So this is the convex mixture of random variables or distributions as you may want to be. Okay, now what happens with this? The thing that happens is that this becomes close to, when n is large enough, okay, when n is large enough, then this becomes close to essentially Px and then Qy1, Qy2, Qyn. Okay, all in tensor. Okay, so this is a kind of a decoupling effect that happens if we consider such a convex mixture. And so the statement is that the relative entropy, so let's call the distribution on the left hand side, okay, to be tau, right? So tau x, y1, y2 up to yn with Px tensored Qy1 becomes less than equal to log of 1 plus 2 to the k over n, where k is the Dmax of Pxy with Px tensored Qy. Okay, and what is Dmax? So Dmax of let me just write it here, is the minimum over C such that Pxy is pointwise smaller than Px tensored Qy. Okay, minimum over, yeah. Okay, so this is the max relative entropy, right? and asymptotically we know that this converges to relative entropy. Yeah, sorry, Dmax epsilon converges to relative entropy. So basically, if we take n to be a little larger than 2 to the Dmax, say 2 to the Dmax over times say 1 over epsilon or something, right? Then this becomes like log 1 over epsilon, which becomes tiny, okay? And then this is relative entropy, and then via Pinsker, then we can go to fidelity, okay? Maybe and L1 and so on, wherever you want to go, okay? Once the relative entropy is small, via Pinsker, we can go to other measures. Okay. So that is convex split lemma, and then position-based decoding is sort of a converse, also can be viewed as a converse, so to say, to convex split. Okay, so essentially the picture is the same. Okay. So let's define one correlated random variable j. Okay. So to this system x, y1, y2 up to yn, let's extend it and define a correlated random variable j, such that when j is equal to I, right? So let me call this component of the mixture is tau I, right? So let's define correlated random variable j, which is correlated to x, y1 up to yn, right? In such a way that when j equal to I, then x, y1 up to yn are distributed according to the ith component, tau I. Okay, and as here the tau x, y1 to yn is convex mixture of tau i's. Okay. Now so the thing is that what is this convex split telling us? Convex split is telling us that if we consider this joint system and if we remove j, forget j out of the picture, then just this marginal looks like decoupled system. Okay. And position-based decoding is about kind of recovery of j if we are just given this ensemble. Okay. All right. So maybe when so let me just informally say here that can recover j as long as n is less than equal to dh of pxy px tensor qy little less than that, so maybe minus say order log 1 over epsilon. Okay, recover j with probability 1 minus epsilon. Yeah, so it's about the recovery of the j if we are given. So essentially, if we are given one of the components of this ensemble, say one of these tau i's, can we actually recover I? Can we do a measurement on tau I to recover I? Okay. But of course, that can only be done if if the number of components of the mixture behave only like dH, okay, which is smaller than Dmax. So essentially, you need more to mix and decouple, but of course, for recovery, you can only recover if they're not too many. Okay, so lesser than Dmax. So you can only go up to dH. Okay, and what's dH? Okay, here I'm going to use dH epsilon. So I'm just writing there exists a measurement M such that I mean the classical case, how should I write it? Let me just use a compact notation anyways. Okay, so we can make a measurement such that it succeeds quite well on the joint distribution Pxy 1 minus epsilon, and it fails badly on the tensor distribution Px tensor Qy. Okay. All right. So that these are the two tools. Okay, so let me remark that there is a close relationship between this convex split tool that I mentioned here to a rejection sampling argument. So actually, our motivation for considering this this convex split arose actually from a rejection sampling argument that we were using, that we used with Jaykumar and Pranab in the classical case and in the classical quantum in the CQ setting to design message compression protocols, and then when we want the fully quantum setting, that's where we sort of needed a more symmetric picture, and that's where that's how the motivation for convex split lemma came up. Okay, so it kind of has a close connection to a rejection sampling argument. Okay, so before I go into the proofs of these, okay, let me mention some of the application that we have been able to obtain using these tools in the quantum setting, and we also tried to write corresponding things in the completely classical setting as well. Yeah, and the completely classical setting, we can get more applications. Yeah. So in the message compression, okay, let me say that this is joint work with Anurag, Vamsi, myself, and this is Anurag, Nakib. Okay, so all right, so the regular one sender, one receiver setting, which is sort of in the quantum setting commonly referred to as quantum state redistribution, and it has its subtasks, state splitting, state splitting, state merging, etc. Then 2 sender, 1 receiver, which is referred to as quantum Kleppen-Wolf. And then there is another sort of an intermediate to quantum and classical setting called as measurement compression, in which, you know, sort of the message is classical. I mean, the rest of it, the operations are quantum, the side information is quantum and everything, but message is classical, and also the shared resource is only public randomness and not quantum entanglement. Okay. So noisy channel. So this is message compression is in the ideal channel setting. In the noisy channel setting, we could give for the point-to-point channel. So this optimal bound, optimal one-shot bound. So interestingly, you know, for the plain and simple point-to-point channel, the optimal bound was not known in the one-shot setting. I mean, actually, the converse was known before, but the achievability was not there. So Gelfand-Prinske channel. Broadcast. Compound channel. Then private channels. This is work by Mark Wilde. And we have also been able to obtain some miscellaneous applications. Not quite related to network setting, but what is referred to as port-based teleportation. And actually a version of matrix Chernoff bound can be obtained from this, which doesn't have like exponentially fast concentration, but polynomially fast concentration. And then some applications in resource theory. Okay, yeah. So yeah, so I just wanted to mention the applications, and in the classical case, I mean, we can obtain more. For example, we can give bounds for, say, multiple access channel and interference channel and so on. But those we cannot handle in the quantum case due to some important bottlenecks. Yeah. Yes, yes, but there is sort of a simultaneous smoothing issue there, which is no. Hope is there, and yeah, hope is there. Yeah, yeah. So, but there is a important technical issue to be overcome there. But if that happens, you know, if that technical issue gets overcome both at the DH and the Dmax end, then a lot more can be done. Okay, so all right, so that does that. 25 minutes, right? So let me first, you know, before coming to the proof of Convex-split, let me first give an application so that we can sort of appreciate the utility of some of these things. So for Convex-split, let me give you a protocol for the one-shot version of simple point-to-point channel. Okay. Okay. So what do we do? So in the point-to-point channel, we have two parties, Alice and Bob, right? Alice gets a message M, let's say in 1 to N maybe, and maybe let me use a different letter, 1 to L, yeah, and then what Alice and Bob can do is they can share. So let me first give you a protocol using public randomness, okay, and then we'll convert into a protocol without public randomness, okay. So the additional property that we will obtain with the protocol using public randomness is that the error, right? Usually the error that is considered is averaged over the choices of the message, right? Say under the uniform distribution or something. But here, for every single message, we will give an error bound. So it's a worst case error bound. Okay. So is we will take public randomness, where random variable X is with Alice and Y is with Bob. Okay. And this is distributed according to some PXY. Okay. And we will take several identical such things. Okay. Yeah. The problem is there is a channel here, right? Some noisy channel which takes input and gives an output here, right? Maybe let's call it X to Z, right? And Alice gets one of these numbers from 1 to N, let's say, and she wants to communicate it to Bob. Okay. And so how large? So given one use of the channel, how large N we can handle? Okay. So the process is very simple. Whenever Alice gets, say, M as some number I, okay. So when M is I, what Alice will do is part of public randomness and feed into the channel. Okay. So then we can see that when M is I, these two have some joint distribution, right? They're correlated, this and the output of the channel. Whereas these guys are all sitting independent. right? So then it's sort of a similar picture there. That is, when the message is I, what the entire distribution, joint distribution of Bob in Z and Y1 up to Yn is like tau I. Okay? It's like the ith component there. Right? Where the joint distribution here is given by, so let me in order to exactly match that, let me call these as Z1 to Z2 up to Zn. Let the channel be from Z to X, right? And what we have here is X, okay? And so the joint distribution Pxyi, right? Pxy will be essentially the channel acting on let's call this distribution as, oh, we are already calling this Pzy, okay, that's our Pxy in that picture, right? And Qy is of course simply Py coming from here, right? And therefore our position based decoding will tell us that Bob can successfully recover I as long as n is dh epsilon of this thing with, let me also say what is going to be Px here. So Px is going to be the channel acting only on Pz, right? Okay, roughly like this, maybe minus order log 1 over epsilon. Okay, now we can see that in the asymptotic setting, so of course what we can do is, because we have the freedom of choosing any Pzy, right? So we can let n to be max over Pzy of this, right? And then in the asymptotic setting, this sort of converges to max over Pzy of I of, right? So this becomes, let me first say D. So this will become D of okay. In the asymptotic setting, both DH and Dmax go to D. So we'll go to D. And what is this? This is, so this is just the marginal of the same distribution on Z, right? So it is a distribution, the relative entropy of a distribution with the tensor of its marginals. So that's the same as let me just say I of x colon y in this, in Z goes to X of PZY. Okay. And here, so this is the way we recover capacity. Yeah. Okay. So I mean, I just wanted to illustrate how sorry, this is Z. This is, yeah. So what is it? So we take a distribution PZY, we add the channel on that, channel Z to X, we get XY, and we just look at the mutual information, right? That's precisely the capacity, and we maximize over PZY. Right? Sorry, what? What? Yeah. No, it's the information of X and Y. Yeah. Okay. Oh, yeah, that's what it's saying. Okay, fine. Right? Okay, yeah, sure. So yeah, so you're saying that we can basically, in this setting, we can set Z equal to Y, right? Okay. So yeah, then it becomes there's a converse. Yeah. The converse for yeah. Huh? No, yeah. But that dies, right? This will die. You mean to say what the second order and so on? Whether one can obtain second order using are the parameters precise enough so that we can obtain second order? Yeah, the lower bound is dH epsilon. This is the lower bound. Yeah, that's it. Up to additive log 1. Yeah, up to. But the thing is that this is precise. I mean, this can also lead to second order. I mean, no. I'm just saying that the first order result is has parameters which are tight enough so that it can lead to second order. Maybe I should just write it like this: PYY I of X colon Y, where there's a channel Y to X and PYY. Okay, so according to the remark of log where. Usually we use n for the block, so basically n for the number of methods. If n is the number of methods, that usually goes exponential, right? I mean, so this is one use of the channel, and then we are asking how large n can be. No, this is one use of the channel. Shall I use a different letter? Maybe M, maybe? Yeah, if yeah, n is the number of repetitions. So maybe just let me use L here. Huh? Log of where? Yeah, that's true. Right, yeah, that's true. So as long as n is not n though, yeah, that's right. You're right. You're right. Log in. Yeah. Okay. Pardon me? Oh yeah. Go back to n. Huh? Put it back to n. Yeah. Okay. So all right. So this is one of the things. So I think one may be able to see a resemblance of this argument with the random coding that Shannon used, right? But except that when one views it in this picture, it sort of first of all, I mean, of course, there are two aspects. When we see asymptotic proofs, I mean the conceptual information theory plus the AEP both come together, and then it kind of mixes issues. So therefore, when we view it in the one-shot picture, the conceptual information theory, sort of nicely separate out from the asymptotic issues. So when we view it in this picture, it is very easy to also consider quantum protocols. Just replace this public shared randomness with quantum entanglement, and then one recovers bounds in the quantum case. Okay. So that is one thing, and now let me come to maybe an application of this convex split in message compression. Yeah, and probably I will not have time to do the proof of it. 5 minutes. 5 minutes. Yeah. So let me do an application to message compression. All right, so let's consider the following setting. We have Alice and Bob, right? And let's say there are two random variables x and m with Alice, okay? And Alice wants to transmit this random variable to Bob. In what sense? So given a particular value for x, Alice wants Bob to sample from mx, okay, from m given x equal to x, okay, define that. Okay, so the only thing that Alice wants to do is when she has x, she wants Bob to sample from m given x. She doesn't want, maybe she has another sample of m itself, but she doesn't care of that, right? She doesn't want Bob to have exactly that same m, but only thing she wants to do is sample from m given x. So for example, if x and m are independent, then there is no communication needed. Okay, Bob can simply sample from the marginal distribution. So now, what can be done, right? What we can do is, again, Alice will have x, right? And they can, using shared randomness. So let me remark here that this is a protocol we gave where there was shared randomness. And now if you don't want shared randomness, the point is that the error is small, right? Error in the entire protocol. In fact, one can observe that the error for each particular value of m is small, right? So therefore, one can always fix a certain shared randomness such that the average error is small, okay? And therefore, one can even get a protocol without shared randomness. Okay, but here we will need shared randomness. So Yeah, it's yeah, like a randomly shared code book. Yeah. Okay, so now what will happen is that Alice, you see, what Alice has with her is like this, right? X tensored, M1 tensored, M2 tensored, Mn, where all of these are distributed according to the marginal M. Okay. Let's use shorthand, distributed according to M. Okay. All of them are distributed according to M. IID. Okay. Now, so therefore, now again using convex split, we can see that this picture X M1 M2 Mn can be extended to create the random variable J, right? So the condition on J, it becomes X correlated with M at the J, condition on J being some value I, this distribution will become X correlated with XM at the ith location. Okay. Now all Alice has to do is create this J and send it to Bob. Okay. Now once Bob has J, Bob can measure J. Okay. And then in that case, this X will then get correlated with Mi condition on J equal to I. Right? Because if it's correlated here, this is public randomness. It gets correlated there. So XMI will then will be distributed according to XM conditioned on J equal to I. And now what is the length of J? So now number of possible J's. So number of possible J's. So the length of the message, let me just call it length J, is like log of Dmax of XM with X tensor M, which asymptotically goes to I of XM. Right? I mean, one can have an epsilon and stuff. But that and all asymptotically, this will vanish. We'll get back this. So we have compressed to the mutual information between X and M. I mean, IID situation, like if you want to do it not in the one shot, but you have like XM, but you have many XM, and you're trying to do it together. So, yeah. So you will, I mean, what you will do is you will run it on, asymptotically you will run it on X tensored, XM tensored N, right, sort of. You will run this protocol on XM tensored N. Okay, so I think maybe I'll stop here. The proof of convex split is also actually easy. Yeah, I could have done that, but we are short in time. So maybe we can take it offline. In the quantum case. So see, the point is that, you know, we have all these Dmax epsilon and DH epsilon, right? Which is saying that we need to smoothen things. So what is Dmax epsilon? Dmax epsilon is Dmax, but you take, you know, not the distribution Pxy, but all distributions close to Pxy, right? And you minimize over that. So that is something that actually converges to the right quantities asymptotically. Dmax itself doesn't converge, right? So you need to smoothen it. Now what happens in multiple, you know, MAC and so on, there is smoothing required across several subsystems, right? Like yeah, I mean, simultaneous smoothing is required because you have a rate region, right? So this should be less than I and this and that. So you have rate region. So all of them. So there is a simultaneous smoothing required. So you need one distribution close to your original distribution which satisfies many properties across several subsystems. No, but broadcast also we are only able to handle two sender, one receiver. One sender, two receiver. One sender, sorry, we are not able to handle one sender, multiple receivers. No. No, yeah, it's only the Martins. I mean, but we can match Martins bomb. Yeah. Yes. Yeah.